Hello, this is Lawrence Master speaking in for Post University's Software Engineering 1 class. We're going to be going through Unit 1 concepts in terms of predominantly understanding what is software engineering. Okay, software engineering in a nutshell is about solving problems. And the reason we need to have a process and practice called software engineering is because software products are inherently typically large and complex. For example, the Windows operating system is many tens of millions of lines long, and without applying some well-known best practices, it would be an insurmountable task to complete. So, in the development process, what we typically do is analysis. We decompose a problem into smaller, manageable pieces, and in that part, abstraction is the key. And then in the second half of solving the problem, we typically build or compose a software solution from smaller blocks. And this diagram here helps us understand a little bit better. Notice this problem here. We can go ahead and if you decompose it into smaller pieces, we can build individual solutions and put it back together into a comprehensive solution for our customers. Okay, so again, software engineering is about solving problems, and some of the nomenclatures we need to be familiar with up front is, for example, what a method is, a tool, a procedure, a paradigm, and this should be familiar to you from previous engineering and software classes. A method refers to a formal procedure or a recipe, and sometimes we can call a method a design pattern. You'll learn some of the design patterns later on in the course, but those recipes are not complete solutions. You kind of have to flesh that out, flesh that skeleton method out or design pattern out into a solution that will fit your specific needs. Okay, and then a procedure is a combination of tools and techniques to produce a product. A paradigm is a philosophy or approach. For example, we have object-oriented paradigms or your traditional structured approaches. We also have paradigms in terms of the processes we use. We can have something called the agile process, or we can use something called a waterfall process to help us in going through our software engineering process. Okay, so what is software engineering and how does it fit into what a software engineering does? Now remember, computer science is more of the invention part in terms of coming up with new compilers, operating systems, and programming languages. Software engineers do not come up with new compilers. It's typically a discipline that uses those tools to solve typically business problems. Okay, so both a software engineer and a computer science um, individual would probably both be very well versed in programming and programming languages and techniques. It's the application of their knowledge that differs. Okay, and this picture right here does a pretty good job of depicting that. You see here, the computer science is focused on theories, and the engineer is focused on tools and techniques to solve a problem. And typically, the software engineer bridges the gap between a customer's problem and theories. Now, in terms of looking back at our progress and how we've done in the past, as we all know, we've done a tremendous job in the past 20 to 30 years of designing software. We just need to look around at the advanced economy we live in, and a large part is due to the advances we've made in software engineering. Now, software engineering is not without failure. We can have faults um, or failures. So a fault occurs when a human makes a mistake called an error, and a failure is a departure from the system's required behavior. So the way this all ties together is that through human error we can create faults which can lead to failures. Some of the more famous software flops in history has been the Sperry Corporation's income tax application, and you could see the numbers here. Amounted to losses in the millions. So uh, software engineering is a complex business. Now, some of the key things regarding what is good software, we can look at it from a transcendental view, a user view, a manufacturing view, product or value-based view, and this is this is more of a philosophical question in terms of what is good software, and really depends on who you're talking to. Some people value software in terms of their resale value, in terms of what customers are willing to pay, whereas others may view quality as conforming to specifications. So you can consider quality in terms of product, processes, or the quality of the product in the context of the business environment. So, so what tools do we have to evaluate if software is good? Well, in the business world, the ROI is a very common method of determining the value of software. So if you meet your ROI, or your return on investment, you could say that from a financial perspective, your software is good. Okay, so moving on in terms of a systems approach to software, we need to understand that hardware, software, and its interaction with people is how we need to go ahead and getting and defining our system boundaries. Okay, so when we move into systems design, it's very important to look at it from a systems approach. And let's just step back for a second. What is a systems approach? Systems approach typically involves activities and objects. So putting some specifics behind that, let's look at our breathing system, our human respiratory system. Okay, so the system has entities which include the oxygen, water, nitrogen, and so on, all the anatomical parts that make that system work. We also have activities in terms of inhaling, filters, and gases, which are part of the functions. Now, applying this to a software engineering practice, we see here we have a systems boundary in terms of this application of creating a payroll application. Notice that the pay information is outside the system boundary, as well as delivering the paychecks. But when it comes to data validation, calculation, and printing, that is the system boundary. So the very first step in really diving into a software engineering solution is really understanding your system and the system boundaries, in addition to the activities and objects as we learned about here. Now remember that some systems are dependent on other systems, so there are interdependencies that make this prior diagram here just a tad more complex. Also, it's possible for one system to exist inside another system. And if the boundary definitions are detailed, building a larger system for the smaller ones are relatively easy. And this is depicted fairly well here in a layered system. And we can see here that the outer shell consists of reporting system for data. Then you have data management, communication systems, computational and processing systems, and remote data collection systems. Moving on to the team environment, we can see that when we talk about the members of the development team, so in the end, your software engineering solution is going to really depend on the members of the development team, and it's important to understand some of those players, which are the folks that do your requirements analysis, your designers, programmers, testers, trainers, maintenance team, librarians, and configuration management team. Each of these individuals have specific tasks that are critical to the ultimate success of your program. Now, in terms of the software development steps, we can see that the analyst maps the requirements and definition, your designer does the system design, and your programmer does your program design and program implementation. Typically, you have testers that do unit testing, integration testings, and system testing, and your trainers will deliver the system and help with maintenance. Okay, so how has software engineering changed? Before the 1970s, it was fairly straightforward. We either had a transformation process, which is where we have input converted to output, or we had a transaction type solution where input was determined, where your input determines which function should be performed. But after the 1970s, we find that we needed to run on multiple systems and perform multiple functions, and that has been further explained by Wasserman and 7 key factors, which includes a shift in the economics of computing. Computing power has exponentially increased while exponentially decreasing in cost. Availability of powerful desktop computing, the emergence of local and wide area networking, graphical user interfaces, and some of the many issues in the waterfall model of software development, which we'll talk about in Unit 2. So this is a great diagram here. As you can see, we got time to market, networking, interfaces, economics, and desktop computing. All those have pushed the complexity of software engineering to a new level. And how do we handle this new level of complexity? Well, we're going to be using abstractions. We're going to be using interface prototyping, which is critical to many of the software development philosophies. We're going to be exercising reuse, measurement, tools, and integrated environments. Now, abstraction involves generalizing your object and hiding details. And we'll learn when we get into our object-oriented part of the course that abstraction is a key idea in helping us develop large-scale software projects. User interface prototyping is another key idea, and prototyping basically involves building a mini or small version of a system. You may be familiar with an architectural prototype where an architect would put out a template in 3D where they actually build a mini tower or a shopping complex. And this helps users identify key requirements of a system and helps develop good interfaces. Software processes, of course, the level of control in the environment varies exponentially as we move from a single user desktop type application to an enterprise-wide application. We find that the level of control is very, very great as we develop applications such as ERP and operating systems, for example. Now, this unit covered some critical ideas. Just quickly reviewing them here. What we want to consider is when we're given a problem to solve, we need to analyze it. And if you remember that picture we saw earlier, what that involves is basically breaking that down into subproblems, and then in the synthesis part, we typically solve those individual problems individually, and we reconstruct it to provide a complete software solution. You also need to understand that requirements do change over time, which helps exponentially increase the complexity of a program. We also need to understand that we need to view quality from several different perspectives. One of them is the value-based view of quality, and then others feel that quality is tied to meeting specifications. We also touched on some fundamental software engineering concepts such as abstractions and prototyping. Those are critical ideas that we're going to be reviewing in great detail as we move further into this course. And finally, please always remember to keep your system boundary in mind. If you have clear specifications of what are your inputs, what are your processing, what are your outputs, those simple ideas will go a long way toward helping you produce a great software engineering solution. Thank you.